thank you so much for joining us for this Day 6 challenge on Advent of Code. It's an honor to have you here, especially because this is a really exciting challenge. If we look at some of the themes we've been covering as part of this series, we've talked a lot about algorithms and data structures. We've even sort of broken down some of the basic data structures in terms of like which situations we want to use them in, whether it's an array, an object, a set. And today I just want to mention that we're actually going to take a look at what I would consider the most efficient data structure in the entire JavaScript universe. So we'll look forward to using that in today's challenge. Let's take a look at what it's actually asking us. So as usual, we have a delightful story wrapping this challenge. And basically the idea is we're given these groups of words. We'll call them words. They're basically strings, strings of lowercase letters. And the idea is that we're given sort of like groups of them. So this one has 3 strings in the group. This one has 2 strings in the group. This one has 4, and then the final one just has 1. And the first one also just has 1. So basically, just like in, I think it was day 4, we sort of have these like multi-line inputs. So if we take a look at our puzzle input, basically each one of these could be multiple lines long. Now, in terms of what we're actually trying to do with these, it's a question of within each group, how many distinct letters are there? Okay, so for example, in this first one, there are 3 letters, A, B, and C. Hopefully that's clear. The same is true of the second one, except it's a bit of a different situation. So this is one where there was just 1 string and it had all 3 of those letters. This is a case where there were 3 different strings and each of them had 1 of those letters. In this case, we would also have 3 letters. It'd also be A, B, and C. However, this is the first case where we see a bit of repetition, right? So the A appears in the first and second string, whereas the B and C are unique to each of those respectively. If we look at this one, so the fourth one on the list here, basically all 4 of these are the same. So there's actually only 1 unique letter, similarly to the last one where there's also only 1 unique letter, which makes sense because it's the only thing we see here. Okay, so basically the idea is we need to go through these groups. We need to find how many letters there are in the entire group. And then basically after we do that for all of the groups, we find the number of unique letters within the group, we're going to add all of those up. So notice we get 3, 3, 3, 1, and 1. Those were the numbers we found as we went through all these groups. And then when we add all of those up, we get 11, and that should be our answer. So let's take a look at how we're actually going to solve this thing. So I copied over just the example as part of our sample input here, and then basically we'll just use our fetch code later on to sort of to put it into the browser console and fetch our actual input, but we'll basically just try to solve it using this example over here. Okay, so I'm going to switch to the full IDE mode, and basically as part of our game plan here, we're going to try to make this work in sort of a naive way, right? This is part of our strategy. We want to make it work first, then we want to make it efficient, and then we want to make it beautiful. Lately, I kind of mentioned this a few videos ago, but lately the functional imperative has kind of been shifted up. We're not really writing a lot of stuff these days that's not functional because we're kind of getting a little more comfortable with the paradigm. So this is maybe less part of the third step. Maybe it's even considered more part of the first step, the second. I'm not really sure. But anyway, the point is we want to make this work first, even if it's not the most ideal way to do it. And then we'll talk about how we could do this more efficiently. Okay, so what are we trying to do? We're trying to find how many distinct letters there are in each group. So first things first, we want to break up the groups so that we basically have like an array of lines of strings, basically. An array of arrays of strings. Let's write that down. Get an array of arrays of strings. And then basically count how many unique letters are in each array of strings. And then basically add up all the letter counts. And that's what we're going to return at the end. Okay, great. So break up the groups. Can do. So let's say groups, we'll just call it that for now. And it's basically going to be our response text dot trim We're remembering that now. Basically, the dot trim is just to make sure we're getting rid of any white space characters at the start or beginning of our response text string. And that could be like spaces, that could be new lines, it's whatever. But the main thing is, just in case there's a new line at the start or end, we want to get rid of that. And then we're doing a dot split on the double new line. So basically that should split each of these things into groups. And then basically those are going to be groups of strings, right? So we could even do a dot map on that and say each group is going to be mapped to group.split /n. Okay, so the single new line character. So what we should get from this is that each group should be an array of arrays of strings. Let's verify that by doing a console log of groups. We'll save this and we'll run the code, and there we go. So actually that looks great. It's much, I consider it much nicer to look at it this way as compared to this. I feel like I can actually dig into this and be like, hey, groups at 2, at 1, and like, you know, it's a lot easier to just sort of directly specify the thing that we're looking for here. So you're probably noticing a big part of these challenges is actually sort of manipulating the data and getting it into a form that we can work with. So that's an interesting thing, because in a lot of coding challenges, we don't really get that so much. Like the input is given to us nicely, and we basically just need to come up with an algorithm to solve it. Whereas in this case, I feel like there's a greater degree of realism. You know, we're actually getting something a little more raw, and that we need to actually find a way to put it into a more comfortable form as our first directive. So that's it's more fun than I thought it would be. Anyway, count how many unique letters are in each array of strings. Okay, so basically what I want to do is write a function to do this. So const, I'll just say count letters, okay? And it's going to take a group, and in other words, an array of strings, right? This is our groups thing over here. So yeah, basically the idea is this is going to take one group, and then it's going to return the number of letters that are in that group. And then basically when it comes to adding up all the letter counts, we're probably going to do something like this, where we say letter counts is going to be assigned the value of groups.map count letters. So we sort of saw this pattern last time, where we have a function that takes an input, which is going to basically represent each of the elements of this outer array. And then basically we're just putting that in for a map. So we could have just easily said within here, like group gets mapped to something, but I think it's a little more organized to just sort of have this individual function over here, which is going to basically run on one of these things at a time. Okay, so basically we want to count the number of unique letters in a group. So how are we going to do this? Well, we could just do something like this and say letter set is going to be a new set. So remember, a set is a type of data structure that is not ordered. So there's no indexing on it. It's not like an array. Lookups are instant, so we don't need to search through it. We basically just say, yeah, that's in there, or no, that's not in there. One way to think about a set is basically as though it's an object that only has true or false values as its values. Okay, so its keys are whatever, like we talked about before, but then its values are just boolean values, just true or false. Okay, we can sort of think about that as being what a set is. So equivalently, we could say that this is like a set that contains A and C, doesn't contain B, right? So this is maybe planting a bit of a seed for something we're going to do later, but I just sort of wanted to think about this way of this perspective that we can take on a set, right? That we can think of it as basically being like an object where the values are just booleans, true or false values. Okay, cool. So we're going to make a new set, and then basically the idea is we're just going to run through each of these strings. Okay, so you know what? It's been a long time. I know I kind of just mentioned that we're going to do things in a more functional way, but it's been a while. Let's do a loop just to sort of very clearly explain what's going on here. So we'll say for const, I'll say row of group. Maybe I should have called that word or string. I don't know. I don't really like to use the word string for this kind of stuff because it's kind of a taken keyword, I think. for const character of row. And then basically we'll just say letter set dot add character. And then at the end of this, return letter set dot size. Okay, so we have dot length for an array. For a set, we have dot size. Okay, so basically, if this works then, if this is going to be okay, what we should expect is basically something that matches up with this example input. So we should expect to see 3, 3, 3, 1, 1, since those were the values that we found with this example. So let's go ahead and run this. And we don't get anything because we didn't ask for anything. That's a nice thing about programming. It'll give you exactly what you ask for, even if you don't know what you're asking for. Okay, so here we go. Hey, not bad. So we've got 3, 3, 3, 1, 1. And I realize I just said not bad, but it actually is bad because this is not functional. So we should probably make this more functional. Now, if we wanted to go ahead and just make it like a dot for each, we could do that, you know, like group dot for each, row gets mapped to row dot for each. Yeah, we could do something like that, but it still doesn't feel right to me. And the reason I say that is because it feels like those functions would be having a side effect. This to me doesn't feel great. The idea of this reaching outside and adding something to this set right here, that doesn't feel great. I would really prefer a way to do this where instead of doing that, instead of actually reaching outside of the set, if it was something where we could actually create the set as we went through. Okay, so basically we've got our group. It's all split up into lines already. Here's what I'm gonna do. This is maybe gonna seem, is this too weird of a way to do it? I'm not sure. We're gonna try this, I guess. So we'll do something like this. Const sets. We're gonna make multiple of these, okay? So we're gonna say this is gonna be group dot map. So for each line of the group, we're just gonna make a new set out of that line. Okay, so what do I mean by that? Basically, we've seen this kind of a setup before, like making a new set from some kind of iterable, right? So we've seen a new set where the input is just an array. Now we're looking at a new set where the input is a string. And what we should find is that just like the spread operator that we've seen before, this is going to do a similar thing. It should basically just take everything from that string and put it into the set as just as a character. Each individual character will just be inside of the set, just kind of floating around in there. Okay, so we've got a set for every single one of these things. And then what we can say is basically just return, let's take an array of the alphabet. Should we do something like that? Yeah, all the letters in the alphabet. So it's just gonna take me a little while to type all of these out. And then once that's all done, we can basically just say that it's not the string that we're looking for, it's the array of these characters that we're looking for. Okay, cool. So this thing, and we're just gonna do a dot filter on this. Okay, so we're gonna say for each character in the alphabet, basically we want to keep, remember how dot filter works, right? We're gonna give it a function that's either gonna return a true or a false for each one of these characters. So it's gonna run on each of these individually, and it's basically gonna say, if it's true, I'm keeping it. If it's false, I'm kicking it. Okay, so basically in this case, what we want to say is if every one of these sets, if every one of these has the property that the set has this character in it, then that's good, right? So we could just do something like this where we filter out all the letters that are in each of the sets. Let's save that and we'll run the code. And now what we're noticing here is something a little weird. So this first one looks okay. The second one does not look okay, nor does the third one, because each of these is supposed to have 3 things in it. So something has clearly gone horribly wrong here. So let's take a look at it. We'll do some investigating. In terms of count letters, so I can see how this worked for the first one. Basically, we went through the entire alphabet here and we said, does every one of these things, oh, you know what? Yeah. That's the problem right there. It's not that every one of them needs to have these. We're not looking for the characters that exist in every one of these strings. We're looking for the ones that exist in some of these strings. Okay, so this is another built-in that we can use for an array. Just like .every is basically going to go through, run this function on every element of the array and expect it to return true for every one of them, some will expect just one of them to return true, and that'll be enough. So if we run this, we should now find that, yeah, there are at least the right number of things in here. Now, of course, what we want to return is not this entire thing, but rather the length of this entire thing. We don't need to know which characters they have in common. What we need to know is how many there are, right? So 3, 3, 3, 1, 1. Yeah, looks good. Okay, good stuff. Looks good. We're happy. So, yeah, was there something else we were going to say about this? Well, actually there is. So the first thing I want to say is this could kind of be overkill. Because if you think about it, well, let's not get ahead of ourselves. Let's keep it this way for now. There might be another way to do this, but we'll just keep it in this style. And well, actually, sorry, I shouldn't say there might be another way to do this. There's obviously tons of ways to do this, like for sure. I'm sure there's a way that we could actually just run like a single reduce on the group and then just directly get the answer from that. That's probably a way to do it. But it's not the way we're going to do it right now. I mean, consider that an exercise for you, dear viewer, if you want to do it that way. We are going to attempt this in a different way, but before we do, let's just take a look at part 2. So I guess we can submit our answer to part 1, and then we'll see what part 2 is asking. We'll give it a shot, and then we'll probably talk about the other way we can do this. So I'm just going to grab my fetch code over here so we can get the actual official puzzle input directly using the fetch API, and then I'll grab this stuff. So the code we had here, and then letter counts should be the thing that we're looking for. Okay, so now letter counts. Oh, actually, it's not the thing we're looking for, is it? It's the thing that we want to reduce. So letter counts is basically really big. It's got 456 elements, and you can sort of see why in this case they're asking us to add the numbers instead of multiply them, because this would be something pretty big. Okay, so in terms of how we're going to add these up, well, at this point, maybe it's not a huge surprise. Anytime we've got a list of elements, so like this big array, and we want to break it down to the point where it's basically just one thing, that is a telltale sign that we want to use a reduce, or that a reduce would be a very good thing to use anyway. So actually here, I'll just say sum and num. Two rhyming argument names, and we'll just say sum plus num and a starting value of 0. Okay. Always good to put that second argument for the starting value, because otherwise there will be an error if your array is empty. Okay, so 6,310 appears to be our answer. We'll go ahead and submit that. And it looks like that was the right answer. Okay, good stuff. So we will continue to part 2. And we'll close this for now. So basically part 2 is something we actually kind of accidentally already did, because part 2 is asking us, well, now it's not how many unique characters there are in any of the words, it's how many characters are in all of the words within the group. So basically this one, well, yeah, there's only one word, so it's got to have all 3 characters. In this second one, none of them have characters in common, so it should be 0. This one, only one character, the A character, is common, so this one should give us 1. So we were actually accidentally getting those values when we had this set to every instead of some. So now if we do this, yeah, we're getting exactly the values we're looking for. So, okay, not bad. Something you'll find in these kinds of problems is that if you set yourself up well in the first part, you'll probably be able to adapt your code for the second part with minimal difficulty. Okay. So that was not a huge change. I think that's got to be a record so far for the least amount of change between the first and second part here. But you know what? I would actually like to do this a different way. So the first thing I want to say is we could probably make this slightly more efficient. Now that we know that every one of these letters needs to come from one of these words, we could actually just say, you know what? Let's actually just take the first line. Line's at 0, right? Or not lines. What did we call it? Group. Yeah, group at 0. So group at 0 should basically just be the first line, right? So we're taking the characters of the first line and filtering those. And that could be a lot more efficient, like when you consider there might only be 3 characters here. So we don't have to go through all 26 of them if we know there's only going to be 3. We would only go through 1 in this case. So that, it could be very efficient because they have to be like, this is not like the other problem where we might think like, oh, but if you only check A, how will you know that there's a B? Well, hey, in this case, if this A is not in any of the other strings, or if it's not in all of the other strings, then like that we're not interested, right? Like, let me put this another way. This B character here, we don't care about it because we already know it's not in the first string. So it's definitely not in all of them. I guess that's what I'm trying to say. So we can afford to just look at the first string here, or the 0th string, or really any of them, but I know there's going to be a 0th element. So that's why I'm saying this. Now, was this really all that more efficient? The answer I would say is no, not really, because this is what I would classify as a micro optimization more than anything. It's not really making a meaningful difference in terms of the actual time complexity or space complexity or anything like that. It might speed this up, well, actually it's ironic because if we take a look at the execution time of the code, it was actually a lot longer the second time. But anyway, maybe that's just a fluke. Yeah, hard to say. But anyway, so basically all I'm trying to say is this isn't the sort of thing that's going to make a meaningful difference in terms of the time or space complexity. So now I want to actually redirect our attention. We're not actually going to solve this problem yet. I want to redirect our attention to something a little bit different. So I said at the start of this video that we're going to look at another type of data structure. So if we think about the data structures we've seen so far, we've looked at arrays, we've looked at objects, we've looked at the idea of a set, and we found that a set could be compared to basically an object that has values that are only booleans, they're only true or false. So then the question is, could we have something like that where the values are just true or false, but where we do have the ordering and indexing of an array? So instead of having like the string key names or whatever type of key names, instead, if we just wanted the sort of like integer key values that we get from an array, but our actual values are going to be booleans, true or false values, we have a data structure for that. And it is the most efficient data structure we can possibly get. It has the maximum level of compression. So I want to show you what it is. So basically what I've done is I've prepared a little spreadsheet with just a quick example over here. Now, I know if you look at the Advent of Code subreddit, you'll find there are some people who use Microsoft Excel to solve the entire problem, which I think is impressive and unenviable. But anyway, that's not what we're going to do in this case. We're just using this to sort of explain the example. So I've got a few words here, and we're looking at basically kind of, this is a data structure that's representing which letters we have inside of each of the words, right? And it's just a true or false, or in this case, like a 1 or a 0. Now, we could have written it as true or false, but seeing it as 1 and 0, actually, there's something about that seems really familiar. Something that I feel like maybe we've seen this in a recent problem. So these are looking a lot like a binary number, okay? So that's basically my claim, that if we want something that has the indexing of an array, but where the values are just true or false, we can actually use just a binary number. Now, keep in mind, like we're talking JavaScript, right? So if we use just a number, like an integer, I should say, then that has a binary representation. So we can store all of this data with no loss in a single integer. In fact, in a regular 32-bit integer, we don't need any like big int, 64-bit kind of stuff. We only need 26 bits in this case, so we're okay. Now, I should have mentioned that before. if this required like 70 bits, if this was like a really long list, like if we were including any type of ASCII character, this probably wouldn't work. Okay, so we've got to be extra careful about this. We wouldn't want to try to use this in a case where it's going to actually overflow the integer size, because we actually would start to lose some accuracy in that case. But in this case, it's fine. 26 is a perfectly reasonable number. So basically the idea is we can do some Boolean stuff with this. I'm basically just going to say assign the value of, let's go with OR. Okay, so we'll use the logical OR. This is like part 1. Did that make it down? Okay, yeah, there we go. Yeah, so this is being assigned the value of true. So I'm just going to say we want the integer value of this. Okay. So maybe we are going to solve this in Excel after all. We'll see. Anyway, there we go. Okay, so 1 0 1 0 1 0 0 0 0 1 0 0 0 1 0 1. Yeah, so if we're to take a look at this and actually add all of these up, there are 6. Okay, so 6 should be the answer for this one. If we're doing it in the part 1 style where it's an OR. Now we could do it in the part 2 style where it's an AND. And now this should change things a little bit. So I think there will be fewer values. Yeah, only 2 of them now. So it's just the A and the T that are common to all of these words. Okay, cool. So basically, that's going to be our strategy here. We're basically just going to represent every word as an integer, which is kind of interesting, kind of freaky if you think about it, that a word can be sort of uniquely represented as an integer. And actually, wait, I just misspoke. It's not uniquely represented, and we can see that right here. For example, the word crate and the word trace contain the same letters. They're different words, but since they contain the same letters, they would actually result in the same binary and therefore the same decimal number. Okay, so the letters in the word are going to determine what the binary number looks like. But that's okay. That's all we need to know about them. So here's our new game plan, okay? Let's write this down. New game plan. This is what we're going to do. So convert. Okay, so this is for each group. Okay, for each group, we're going to convert each line, each word, I'll put it in quotation marks because we know it's not actually a word, but more like a list of letters. Anyway, so convert each word to a number. And I'm just going to use the word bitmask over here. I think I'm using that word correctly, but I might not be. Basically, the idea of like converting something that's a list of Booleans into just one binary number or one decimal number, I believe that is called a bitmask. But anyway, it might represent something more specific than that, in which case I apologize. It would not be the first time I've told you something wrong. Okay, so convert each word to a number. What do we want to do after that? Well, basically, for part 1, do an AND operation. Do a bitwise AND on all the bitmasks. And then basically, it was a bitwise OR. That was part 1. And then for part 2, do a bitwise AND on all the bitmasks. Okay, cool. And then basically the final thing we're going to have to do is to basically convert back from this. So when we just had like a list of all the letters that were common to the words, that was pretty straightforward. Like if we had all the letters, we could just do like a dot size or a dot length. Like we could find how many there were. In this case, it's going to be a little more complicated because we're basically going to be given this binary number represented as a decimal, and we need to know how many set bits there are. So that part's going to be a little strange. We're going to have to basically search through this and find how many ones there are in the binary representation. We'll look at 3 ways to do that. So, okay, let's switch over to our full screen IDE mode. Yeah, so basically find the number of set bits in each result, I'll just say. And when I say the result, I mean like whatever we get from this or whatever we get from this. Like, yeah, you know what I mean, hopefully. But anyway, okay, for each group. So we have all the groups over here, right? It's really, I guess, just the count letters function that's really going to drastically change here. So let's work on that. So for converting each word to a number, I guess we'll make a function for that, and we'll actually start with a function for just converting a character to a number. So character to binary is what we'll call it. It's going to take a character. And you remember the bitwise shifting we were looking at in the last video? If not, basically it's this. So if we have a binary number that's like 101, in fact here, I'll just use this as an example. 101, and we bitwise shifted over by 2, then we're basically just doing this. And I'll just put the spaces in here to better illustrate. Yeah, so basically this is left shifting it by 2. Okay, so it ends up being this number over here, which would be like 0, 1, 0, 2s, a 4, no 8s, and a 16. So this would be the number 20. Okay, so we're bitwise shifting it to the left. Now in this case, we want to start with the number 1, and we want to shift it over so that it's basically just going to be either 1, or it's going to be 1, 0, or it's going to be 1, 0, 0, or it's going to be 1, 0, 0, 0, 0. Like, you're getting the point. Basically, we just want to shift this over how many times? Well, basically something that's just going to be unique to what this character is. So we're going to say character.characterCode at, that's a JavaScript built-in, and it's basically going to give us the ASCII code of this character. If we don't specify an argument for this, is just going to take character 0. And there's only one character here, so I'm being just slightly more efficient by not putting that in. And then I'm going to subtract from that 97. Where am I getting 97? Well, I know that all of these characters are lowercase, and so I'm just doing lowercase a character code at. That's basically what I'm doing. I just happen to know that this one is 97, so I'm just going to replace that with 97. Okay, cool. So that's just for a single character, right? So keep in mind, it's basically going through what we were looking at over here, but if it's just one character, there would just be a 1 somewhere here and then a bunch of zeros everywhere else. Okay, so that's how we get a single character. Now let's do an entire word. So const word to binary. And in this case, we'll start with a word. And we want to break this down. Let's do this in parts. So we'll say something like this. Okay, we'll get all of the binary values. So I'll say const binaries is going to be assigned the value of basically all the characters in the word. And then we're going to do a dot map on that where we just say character to binary. Okay. This is another one of those situations where we could be like, oh, well, we'll say character and then, whoops, I thought I was typing. We'll say character and then that gets mapped to character to binary with an input of character. But like, think about it. That's what we're already doing by just saying character to binary, right? Because this is going to say, oh, you've got a function there. Well, I'm going to go through this array and look at every element and use that as the input of this function. Are you expecting that? Well, yeah, we are. We're expecting a character as the input to this function. So we're all set up. We're as set up as we need to be. Everything's good and everyone's very happy. Okay, so basically what we're going to do with this is a reduce now. So we're going to return bins or binaries dot reduce. I love a good reduce. We'll say, what should we call this? Result? I don't really like using result for this, but oh well. If you think of a better variable name, feel free to suggest it. Okay, so we've got result and then we've got the binary that we're looking at right now, okay? So basically, this is something that's going to go through and we want to do, actually, hold on. Let's put a 0 there just for placeholders so there aren't any errors, but just to show you what I mean, like, let's say we had a few different binary numbers here. Yeah, there we go, okay? So basically, this is 8, this is 1, and this is 2. And I want to add all of these up. I want to amalgamate them. There are a few ways we could do this. Since we know that they're going to be like unique, they're going to be exclusive. We know that basically we're going to have a 1 and then everywhere else in that column, it's going to be zeros. So we could just add these up, but really the proper way to do this would be bitwise OR. So we go through one column at a time and say, well, is this one 1 or is this one 1 or is this one 1? And we'd say, yeah, the first one is. So yeah, it's definitely 1. And then we do the same thing with this. Is this one or is this one or is this one? Well, no, actually, all of those are zeros. Then we go through and say, is one of these 1? Yeah, one of those is 1. The last one is. And then for these, one of them is 1 because the middle one is. And so that's basically what we would get as a result if we were to do a bitwise OR on all of these numbers. Now keep in mind, the numbers will not look like this. So I just want to be absolutely clear. Like the numbers would look like their normal numbers. They would look like this one would look like 8. This one would look like 1. And this one would look like 2. Now, if we take a look at this, basically this is 11. It's a 1, it's a 2, it's an 8. So basically the idea is that like the way we're actually going to type this out, or the way we're actually going to work with these things is like, 8, and then bitwise OR, and then let's say 2, and then basically this would give a result of 10. So like all the binary stuff that's happening, all this like bitwise, looking at the columns, all that stuff, that's like behind the scenes. We're not ever gonna see that stuff unless we were to do like a .2 string and then put a 2 in there for base 2. So like we're just gonna look at these numbers normal in the decimal way that we're used to, right? We're gonna look at, like this. This is if you did 8, and then bitwise OR with 2, it would give you 10. Okay. If anyone has any questions on that, feel free to leave a comment below, but that's basically what we're doing with this stuff. So for this, we want to start with 0 as our initial value for result. And then we're just going to say result, and then bitwise OR, and that's it. That's all there is to it, I think. We'll find out. But basically the idea is maybe what we'll do for now is just a console log of all of our inputs. So we can take our groups and then just do a dot map. Is that going to make sense? Let's see. Right, we want to do that on one of them. So it's kind of like the count letters that we're replacing here. So maybe we'll just do a count letters on the first group. Or actually, here, we'll do, okay, hold on. Let's just remind ourselves what groups looks like. First things first, right? Okay, so there's groups, and it looks like we're console logging letter counts as well. So let's just get that out of the way. Okay, so we've got our groups. It's these things. Okay, so what we actually want to do is run this code, this like word to bin code on some of these. Okay, so let's actually just do that. So word to binary, and the word is just going to be ABC. Let's try that. That should be fun, and it gives us a result of 7. Okay, now you may recall 7 is the result we would get if we had this. Okay, now I doubt that's exactly 23 zeros, but it, that's what it's intended to be. So this is basically like our ABC. We have 1A, 1B, 1C, and then 0 of all the other ones. Okay, so notice it's not telling us the number in binary, but we can still use this decimal number to perform bitwise operations. And I shouldn't say we can still use, like that's how we do it. Okay, cool. So our word to binary, it seems like it's working. Let's just say AC for advent of code, and we'll see if we get what should we get in that case? 5, I guess, because that would be like 101. So yeah, we should get 5 from this. Okay, great. Now we should get some huge number by just putting in Z, and it should be basically an enormous power of 2. It should be like 2 to the power of 25. And yeah, I believe that that's a power of 2. Okay, cool. So I think word to binary is working. Now, here's another interesting thing that we could say. Just as a quick test, let's do this. So Z is the first word. Let's just say A is the second word. And what we should expect for this console log is 0, because this is basically like 1 0 0 0 0 0, and then this is like 0 0 0 0 1. So basically, every column we look at is gonna be zeros. Right? It's going to have at least 1 0, and we're looking at an and. So we should expect this to be completely 0. Yeah, it's 0. Now, if they did have something in common, for example, if this was AZ and this one was just A, now it should be not 0. In fact, I think it's going to give us 1, because A is like the 1 where they agree. Now, if we made it like, let's say cat and bat, okay, then basically the A and the T should be common to each other. So we'll get some number, and it's going to be a big number because 0 to the power of whatever character code T is going to be large. And then we also have the 1 that we're adding to it. So yeah, there we go. Not quite a power of 2, but close. Okay, so basically all I'm trying to show is that this is giving us some kinds of values, okay? Now, we could actually look at the binary representation of this if we wanted to. We could just take all of this and do a .toString on it. So let me just make sure I have the right part. Yeah, I think that's good. .toString of base 2, okay? So there we go. Now notice it starts and ends with a 1 and it's not 26 characters. That's just because it's getting rid of all the leading zeros. It's not considering the leading zeros, and that's okay. All right, so basically this is trying to show us that we can sort of represent our words as stuff like this, okay? Stuff like in what we have in this table, and then we can use that to really efficiently come up with this like combined value. When we compare that to what we were doing before, the idea of like, oh, let's just take every word and make it into a set, and then let's just go through the whole thing and do this .every on every single one of these things. Like, it's incomparable in terms of efficiency here, right? Like, not only do we have the most minimalistic data structure that we could possibly use coming out as a binary here, but in addition to that, now the comparisons we need to make, we don't need to be like, okay, let's go through these arrays and look at every single element and see if every single one of these has them. No, all we have to do is just one bitwise operation. Well, 1 for every line of the group, but like, you know, that's pretty good. Okay, so let's get our count group function in here. So this is going to be something that takes a group and basically finds the count letters. Count letters is what we called it before. Maybe we should call it that. Well, this way they'll be called different things, so that's probably okay. It's probably okay. Okay, so basically count group is going to take this group. Now remember, a group is an array of words, right? We can convert those words to binary, and then we can basically take all of those resulting binaries and combine them all using our bitwise OR operator. So let's do that. Okay. So, sorry. This is where we would use the bitwise OR. And we're in part 2 now, so we're going to use the bitwise AND. Or I guess we could do both of them, but anyway. Okay, so first things first, we're going to go through our group. So we'll say group.map, and for each word within the group, we're going to say word to binary. In fact, we could just say group.map and then word to binary, right? It's a function. I think that should work. Okay, so that's basically going to convert it all into binaries. And then from there, we could just do a .reduce on that and find the ones where they are all present, right? So basically, well, actually, hold on. Let's just do this one step at a time. So this thing right here, this is all of our binary numbers, right? Just to make sure we're on the same page. Let's return binaries. So we'll do count group console log of count group with just the first one. We'll just say groups at 0. Yeah. Okay, so we're getting 7. Groups at 0 only had 1 word, so it's not the most interesting example. Yeah, maybe we should add on that example that we had in the other place. Yeah, so we had like take, trace, cat, and crate. So let's use that as our first example. And yeah, so there we go. Now this is really, this is enlightening actually. So we're getting 4 different numbers, and they kind of just look a little garbagey, you know, like what? Like, how do these represent these words? But we sort of saw that these are like decimal representations of binary numbers. Now, if we were to actually do a dot map on these and then show that actually these are, like show these as binary numbers, then that might be a little more clear. So we'll say num.toString 2. So base 2 because they're binary. So Yeah, there we go. So this is maybe a little more clear, like where all of these things are coming from. Now they are kind of backwards. So like the A has been shifted the fewest number of times, so it's actually the least significant here, but it doesn't really matter. I mean, at the end, we're just going to count how many ones we have. It doesn't really matter if we have these backwards or whether we even consider this backwards. Okay, so I'm assuming this is the character T and this is the character R over here. Some of them had an R, some of them did not. All of them had T and all of them had A. And so when we combine these, we should just get these ones from the T and the ones from the A, and then we'll just have like a 1 0 0 0 1, and then we'll run our function for counting the number of ones, and that should give us 2, and everyone will be very happy. So, okay, basically our plan here is that we've got these binaries, so we've converted all of our groups, all of the lines, all the words within the group into binary. Now we need to combine these according to what the problem's asking for. So for part 1, we used an OR. For part 2, we're going to use an AND. So we could do both of those. Basically, the idea is that we're going to do something like this. We'll say const result is going to be assign the value of binaries dot reduce, and we just want to put all of these together. So we'll say I can't use result again. I'll just use, what would be the result? I'm trying to think of like a word like sum or product, but that's the result of doing a bitwise AND operator. I don't know if we have a word for that, but let's call it, well, it needs a name. Let's just call it Andy for now. And we'll call each of these just binary, okay? And we'll start with a really big number, actually. We want to start with a number that's basically like ones everywhere, right? Because otherwise, if it was zeros everywhere, then all of these would disappear when we do a bitwise AND. So we need something that's like ones everywhere. I'm going to use kind of an interesting property to illustrate how we're going to get that. So if we had this number in decimal and we subtracted 1 from it, we would get this number, right? So similarly, if we had this number, or if we had like, something like this, let's say, and we subtracted 1 from it, then we would have something like this. So we're basically like taking away this 1 and then replacing everything after it with like the biggest possible digit we can. So similarly, if we had a binary number that was like this, which I think is the number 40, then we could subtract 1 from that to get the number 39, and it would look like this. Okay, so basically all I did is, it's kind of like if you see 1,000, you take away 1, you've got 999. With binary, you see this 8, you take away 1, you have 7. But then in addition to the 8, we also have this 32, which is why the number is 40, and then this number is 39. So this is a property that we can use. We could basically just come up with like a really big number, like 1 and then 26 zeros, and then subtract 1 from that, and it should just end up like 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And like, yeah, we could just put in that number directly. We could be like 0x 1, 1, 1, 1, 1, and that's a possibility. But instead, I'm just going to do this. We'll say 1 left shifted 27 times, and then we'll subtract 1 from it. Okay, so it's just going to be that. Now, we'll have to switch this up for the for the OR version of this problem, but for now we'll just do the AND version. Okay, so we'll say Andy and bin. I'm not really liking this temporary name, so I'll just call this total. That's probably better. Total. It's not really a total because it's not like we're adding these up. Anyway, we're not going to worry too much about the variable name. We're just going to say return result. Okay, so basically, if we do count group for the first group, we're no longer returning a list of items. We should now be returning something that's the result of amalgamating all these. And I guess I'll just say, maybe down here, I'll do a .toString with base 2. So we'll save that. And now we do find that there are exactly 2 set bits here, and it's going to be the A and the T character as we found earlier. Okay, so this is good. This actually bodes well. I'm happy about this so far. It's a very surprising use of binary. I doubt we expected to use binary numbers when we began this problem, but that's part of what's so exciting about it. So here, let's move this up. So let's call them, I want to basically come up with two of these functions, and one is for and the other is for or. But before we do that, maybe we can make this a little more efficient. So really, like if you think about it, bins, binaries, is just this. It's group.map word to bin, or word to binary. And this is what we're returning. So like we could get rid of absolutely everything else and just say this. Which, I don't know if that's an improvement or not, but it looks decent. It's giving us the right value here. It's possible that we could actually even get rid of the map and just go directly to the reduce. And the only issue here is this is not a binary. This is a line, or actually it's a word according to the terminology we've been using. So then we can just say like word to binary of word and put it in there. So we can do all of this within the reduce instead of doing a map and then a reduce. Now, I'm not exactly sure which one would be considered more efficient. I know in some languages, for example, in the functional language Haskell, it uses something called lazy evaluation, which basically means if we did have like the dot map here first, and then a reduce after it, it would actually look ahead and see that and combine them itself, right? So like it would basically come up with the most efficient way to actually do the calculation. I don't believe JavaScript is making any such considerations. So I'm not sure what would be better in terms of doing the map first or doing the reduce all in one. It's really up to you, but we're going to call this count group and, okay? And then basically we'll do the part two part. That's not the right indentation, I don't think. Okay, so basically we're just going to take this, I'm going to copy the code, and I'm going to make a couple of slight adjustments. So first of all, this is going to be called, well, actually that one, if we're going in order, that one should be called and this one should be called or, because that was the first one we had to do. Okay, so the first thing we're going to do is instead of an and, it's going to be an or. And then the other thing is, instead of this being like all ones, this is going to be all zeros, which is actually a lot more straightforward. We just make it a 0. So let's save that. And now let's see. So we no longer have count group. We have count group or and count group and. So if we do this one, there should be many more ones. Yes. Okay. Just the right number of ones, I think. Yeah, it's 6. And that was what we found when we were looking at this. And I guess it's no longer on screen. But when this was an or, and then we sort of extrapolated that to the rest of these, we found that the total we get is indeed 6. So looks like we're doing something right. That's good to see. So that's count group or, and now let's do count group and we should expect to see that like, well, basically this. Yeah, it's looking good. Okay, so I'm happy with this so far. The only problem is we actually haven't completed the problem because we haven't yet found the number of set bits in each result. Okay, so we've got a lot of nice functions like actually hold on, convert a word to a number. That's what this one does. And this one converts just a character to a number. A binary number. Okay, cool. So that's, I guess I don't need to say new game plan anymore. So yeah, okay, cool. Letter counts. That's part of what we were doing before. We had count letters. I'm gonna be honest, I don't really like this code as much, so I'm gonna go ahead and delete that for now. Yeah, this is looking much better. So basically, we've got our groups here, we've got our function for converting a character to binary, our function that builds upon that converts a word into binary, and actually I am sort of noticing like binaries is just this thing right here, right? So maybe we actually just want to put that in, and since that's the one thing we're returning, we can make this look a whole lot more efficient. Or, you know, it can look smaller, I guess is what I'm trying to say. Okay, cool. So then the only thing we need now is something that actually counts the number of set bits in a group. So let's do that. And actually, sorry, I shouldn't even say that. Something that counts the number of set bits in a number. I mean, that's what it comes down to, right? Because these things, like, these are giving us binary numbers. We need to actually count the number of, and actually count group is kind of a misnomer here, I guess. So yeah, basically, this is something that's going to take a binary number and it's going to return the number of set bits in that binary number. So this is going to be a recursive function. The way it's going to work is, I'll just call it count set bits. And it's going to take a binary. And yeah, basically, we're going to say, is this binary number equal to 0? And if it is, we're just going to return 0. If it's not, we're going to return one, well, something. We'll see. So basically, the thing we're going to return is another call to this function, count set bits, except now instead of using the same binary number, we're going to use that binary number shifted one to the right. So if we shift this number to the right, eventually it's going to go down to 0, right? And we might have like 1 0 1 1 or something. We shift it to the right, and now we have like 0 1 0 1. We shift it to the right, we have 0 0 1 0. Shift it to the right, we have this, and shift it to the right, we're at 0 now. So eventually, if we keep right shifting, we'll get to 0. The question is, do we want to add 1 to this? Like, we're going to call this other function here, but do we want to actually add 1 to this? Good question. So the way we can say that is basically binary and 1, right? Whatever this binary is, we're going to compare it to this number. So we'll just say, like, looking at this first one, yeah, well, these two would AND to a 0, these would AND to a 0, these would AND to a 0, but really it's just the 1 we're comparing, right? So looking at this, that would be a 1. Whereas if we compare it to this one, we'd have zeros everywhere, and then comparing it to the ones column, we would actually have a 0 from this 1 and 0. So basically the idea behind this over here is this is a part that's only going to be equal to 1 if that bit is set, okay? So it's kind of like it's a lot like a loop if you think about it. Like we're basically starting with a number, yeah, like this number, for example, and just saying, hey, is this a 1? Oh, it is? Oh, okay, well then add 1 to the total. And then look at the same thing, but with this number now. And then we say, is that a 1? Yeah? Oh, okay, add 1 to the total. Okay, and now look at this number. And is this a 1? Oh, no, it's not. Okay, add 0 to the total. And then, is that a 1? Oh, yeah, it is. Okay, add 1 to the total. And then we look at this number and we say, oh, that's not even a number. That's 0. Well, sorry, 0 is a number. But like this doesn't have a non-zero value, so we're just going to return 0. So then that'll complete this function call, which says, oh, okay, we got 0. And what did we all want to add to it? Oh, we wanted to add 1. Okay, so we have 1. And then we were going to return that for the previous call. And we say, oh, okay, cool. So this gave us 1. What are we going to add to it? A 0. Okay, so we still have 1. And then that returns the previous call. And that says, oh, okay, we got 1 from that. What do we want to add to it? Oh, we want to add 1. Great, so now we have 2. And that goes back to the previous call, and then that says, we got 2 from this. What did we want to add to that 2? Oh, we wanted to add 1? Okay, great. So we have 3. So basically, this will go through, and it's going to count all the set bits in our number. Now, we are getting a number out of this. So basically, we just have to do count set bits on this thing. And same thing up here. So for each of our count groups, whether we're using an AND, whether we're using an OR, we're going to have to actually do the counting. So count set bits. So that's another nice reason to use a function, right? So that we don't have to repeat ourselves. This is all looking very nice and functional, I must say. Okay. Hey, why'd you indent those? That's not nice. Okay, great. So let's save that. Yeah, we got a little bit of rearrangement over here, but that's okay. This dots2string thing, I don't think it's going to work anymore because we're actually counting the group. So count groups, and we should get 2 from this, right? Because we should actually have like the number of ones in the binary number. So there we go. We got 2. So now let's say instead of AND, let's try it with OR, and we should get 6 if I recall correctly. Let's find out. It's 6. Okay. Now let's do the full input. So we'll say groups.map, and yeah, just count groups, or let's start with that one. We had like, I think it'll be like 6 3 3 3 1 1. Yep. And then we'll do count groups and this should be 2, 3, 0, 1, 1, 1, I think. If I'm just trying to remember that from the previous ones. Yes, so 2, 3, 0, 1, 1, 1. Perfect. Okay, good stuff. This is looking good. Now, we are almost done here. And I've got to say, I mean, I love what we see. You know, the fact that we were able to use the absolute most efficient data structures in the entire JavaScript universe, that is very exciting. It always feels good to use bitwise tricks, and actually there's kind of a whole subset. You know how like regular expressions are kind of like a language, like a miniature programming language in and of themselves, and we can sort of port those into various other programming languages. So there's kind of a similar thing. Since so many programming languages use binary and have things like bitwise operations, there are actually things called like Bitwise hacks that people learn in order to like really efficiently manipulate binary numbers. And we're going to learn one of them today, actually. This is one I came across fairly recently. It's called Brian Kernighan's algorithm, named after the Canadian computer scientist from Toronto, Ontario. And it's used for exactly this purpose, finding the number of set bits in a binary number. And it's going to be just slightly more efficient than this. If you think about it, this is, no matter what, it's going to go through the entire binary, right? So this could be like 26 ones, right? And it'll go through the whole thing. Or it could be like a 1 and then 25 zeros, and it'll still go through the whole thing. So we want, ideally, something that's going to be a little more mindful of what the number actually looks like. So we're going to do something that builds on the trick that we saw earlier. So remember, if we have a number like this and we subtract 1 from it, then we get this number. Okay, so we'll say this is like n up here, and then this one is n minus 1. Okay, so then the question is, if we did a bitwise and on this, and actually here, we'll do a nice horizontal rule here, and we're going to get some result here that's going to represent n, and then bitwise and n minus 1. Okay. So let's actually fill this out. So for the first column, 1 and 1, yeah, that gives us a 1 according to and. The next column, 0 and 0, that's definitely a 0. 1 and 0, that's also a 0. 0 and 1, that's also a 0. And it's also the rest of what we have here. So basically, notice what just happened here? Like, take a look at the first number. Now compare it to this number. That's interesting. Basically, the least significant set bit has just been removed. Now, maybe that's a coincidence. Let's try it again. So let's take this number. Okay, so that's like our n minus 1. But this is like our new n value. And we're just going to subtract 1 from that. Okay, and then we're going to do a bitwise and on this. And it's all zeros. So it looks like if we do n bitwise and n minus 1, thanks to Brian Kernighan's result here, we can use this to basically remove the least significant set bit from our binary number. And so basically we can just keep doing this until there are no more set bits and just count how many times we had to do it. So in the worst case, this will end up being as bad as going through every single one of them. Like if it was 26 ones, then yeah, we're going to go through every single one of them. But if it's a 1 and then 25 zeros, this is only going to fire once. So that's a lot better if you ask me. So let's do this the Brian Kernighan way. We'll use this recursive function for sure, except we're going to do it a little bit differently. So this, actually even this is going to be the same. We're going to ask, hey, did you still have that binary number? You still have some sort of value there? Okay, well, if you do, then repeat this calculation, count set bits, with which number? Well, basically whatever that binary was you were just working with, bitwise anded with itself minus 1. And then we're going to add, what do we add to it? You know, we could do some sort of like bin and 1 or something like that. But the thing is, we actually know that we just got rid of a set bit. So we have to add a 1. We know every time we call this function, we're getting rid of one of the bits. So we might have expected this to look more complicated, but it's simply not. I mean, this is a more efficient function. It looks just as... Oh, whoops. Did I miss a parenthesis somewhere? Yeah, I guess I must have, eh? Okay, is this happy now? Yeah, it's happy. Okay, and so am I. Great, so that was for and then we'll switch this over to or for just a sec. And yeah, still getting the correct values. So, oh man, what a rich problem this has been. We learned about a nice, very cool Bitwise hack. We learned about a new way that we can sort of envision a problem that doesn't really seem inherently like it has anything to do with binary, and actually use binary numbers as just an incredibly lightweight and efficient data structure. So this is really nice stuff. And, you know, I don't know if this is just a coincidence, but these numbers over here, the run times are looking nice and small here as compared to what we were doing before. So I'm happy with this. I hope you're happy with this as well. I think I'm ready to basically just copy all of this code and, oh, wait, let's just get the fetch code first. Yeah, let's go over here into our browser. So I'll get the screen split again. We'll put these in here and I'll grab the day 6 code. We'll just copy that and paste it in over here. And then basically, let's see, we want to call count groups. Well, should we call count groups or first? Or actually, sorry, we want to do, yeah, like groups dot filter? No, groups dot map. Yeah, sorry. Count groups and. Oh, count group and. Yeah, sorry. Groups dot map with that. Okay, right. And what we found was that we actually needed to do a dot reduce in such a way that was going to add up all these numbers, starting with a value of 0, and we get 3193. Now, was that actually our answer for the first one? Not even close. Well, oh yeah, because the first one was count groups or. Whoops. Okay, here, let's try this now. So if we did or instead of and, yeah, 6,310. Oof. Started to sweat for a second there. Anyway, 3193, I think that was the answer we got, right? So we'll go ahead and submit that. And oh, that is extra tasty. Okay, nice stuff. So folks, I've got to say, I'm very happy with this, and I'm extremely proud of you for making it this far. These kinds of Bitwise tricks are just so much fun. And I mean, like, the thing about these is you're not going to find a more efficient way to do this kind of stuff, right? In terms of data structures, like, it's basically like we're dealing with these things at the molecular level, right? Like, we're talking about the zeros and ones, like the guts of the computer, right? And maybe at the subatomic level would be an even more accurate comparison. But anyway, looks like we're done here. We found a nice way to do it. It was an efficient way to do it. I'm happy with the result. I hope you're happy with the result. And I'm so looking forward to seeing you in the next video. I'm sure it's going to be a great one. In the meanwhile, remember to believe in yourself. Anything's possible. I'll see you next time. Bye for now.